I thank the authorities in this institute for the excellent hospitality, senior and junior workers. And I also thank Professor Deshmukh, who was very keen on having some of us. In fact, about nearly 30 years back, when we did some work on the revised planetary model by Neelakanta Somayaji, which was just mentioned by Ram Subramaniam, MD Srinivas, and we told Deshmukh about it, and he was kind enough to include it in the syllabus, for the classical mechanics course for the undergraduate students. So he was kind enough to introduce them to the topic, though we are not that well known. And normally, if you make any claim, at those times at least, you are highly suspicious. People, especially in the scientific community, are extremely suspicious about any claims about very important things being done in the country in the past. Okay, so at that time he was kind enough to include that. Okay, so my talk is on the nature of the Indian astronomical tradition. Yeah. So Bharatiya and modern systems, the nature of discussion on the knowledge systems, including comparison with the prevalent modern dominant systems, would vary depending upon the nature of the discipline considered. In disciplines like agriculture, water management, medicine, or architecture, the differences between the Indian and modern methods are glaring. For instance, there is a clear-cut distinction between the characterization of a disease and its treatment in modern medicine and Ayurveda. In the former, the diagnosis and the treatment are at the molecular biological level, whereas in the later, that is in the modern system, it is the molecular biological level, whereas in the Ayurveda, they are based on the very different concept of balance of three doshas in the body. See, Vata, Pitta, Kapha, you have heard about it. In more theoretical disciplines like astronomy and mathematics, very clear-cut distinction in the sense of this method in total contrast to that method may not be there. But there are distinctions, there are distinctive features. So for instance, this is the diagram of a celestial sphere. You see what you see on the sky, sky and in the night, when you look at it, it will look like anytime it will look like a hemisphere, right? And in the night you can see the objects clearly, apart from sun and all that. So this hemisphere is called a celestial sphere, and in India it's called Khagola in Sanskrit text. The uppermost point is zenith. Now it's called zenith. We call it Kamadhya. The north celestial pole was called Dhruva in Indian text. Then the horizon is Kshitij. Then you have this equator, celestial equator, which is parallel to our equator, you see. So that is at any this celestial equator, that will be inclined to this vertical by the latitude of the place. So that's called celestial equator nowadays. It was called Ghatika Mandala or Ghatika Vrutta or Vishuvat Vrutta. Then ecliptic, that is the path in which the sun, moon and all that move, planets, they move close to the ecliptic. Sun moves on the ecliptic by definition. That's called Kranti Mandala. The declination, how much is the sun varying from equator, okay, how much is this, that is called Kranti. So like that, and that's what is known as 6 o'clock circle. So that is, any body will rise in the eastern portion of the sky, any celestial body like sun, moon, planets, stars, everything. It will go up in a circle and then come down, okay. So that is called a diurnal circle, and that is called in India Ahoratra Vrutta. And when it comes, you see, when it goes up, it reaches the middle circle, you see that vertical circle, so that is called meridian. Now, it used to be called Yamyottara Vrutta or Dakshinottara Vrutta in Indian texts. So from there, you see, when it comes down, how much time? You see, time can be measured in degrees or hours or ghatikas, okay? degrees means 360 degrees is equivalent to 24 hours or equivalent to 60 Gatikas. So, when it comes to this circle which I have written as 6 o'clock circle, that is called Unmandala, it would have covered 90 degrees. So, from the meridian to that circle, so that is 90 degrees or 6 hours. So, that is how it, so concepts are similar. So, the objects and variables of interest in Indian text and the initial phase of modern spherical astronomy before celestial mechanics are the same. Okay. Of course, after this 18th, 17th century, things are different. Okay. They talk about celestial mechanics. But before that, what was there, and much of it is of, Indians were already using it, those kinds of concepts. I will come to that in a little more detail. So, the terminology in Sanskrit regarding celestial objects is mostly directly mappable to modern terminology. Similar things are calculated, but in different ways. For instance, the shadow of a gnomon, okay? So, one vertical stick. So, you shadow of this thing, when sun's rays are coming, the shadow of the stick is observed. From the length of the shadow, one can find out the time, you see. So, that is given as a very important topic in Indian astronomy texts. It's called a gnomon or vertical objects. So, methods to calculate are different in details, quite a bit, at least especially in the olden Indian texts. The method to actually calculate that, and it is directly related to time, is different from the modern this thing. But the overall result are the same, okay, because both the calculations, if both of them are correct, then, they should be the same. And similarly, calculations related to eclipse, beginning, middle, end and all that. So, there are similarities. I mean, similar things are, astronomy is astronomy, okay. So, similar things are talked about, but however, Indian astronomy has its own distinctive characteristic, that is a sutra format. So, quantitative astronomy as a scientific discipline in India can be traced to Vedanga Jyotisha around 1250 BC. This is in the sutra format, or it's called, it's algorithmic in nature, okay. So, you get short rules for various calculation of various things. Okay, Vedanga Jyotisha, if you remember, was mentioned by Professor Sriram also. So, it is, you can say, the first mathematical astronomy text. Mathematical means it is not, I will come to that. It is a simple mathematics at that time, what can be called arithmetical astronomy. So, here you have a 5 yuga. Avinash Chandra Pandey was just now telling that you have got a Mahayuga of 43,20,000 years and 1,000 such is Kalpa and all that. But in beginning, even before Vedanga Jyotisha, they used to have a concept of 5-year yuga, short yuga, okay. So, if you have a 5-year yuga, 1830 days, in that there are 1830 days, so which consists of 60 solar months, 67 sidereal months or 62 lunar months. So, we have a calendar. Earlier also it was there, calendar concept was there in Vedic text and all that. But here says mathematical kind of a calendar, which is precise rules are there. So, we have 60 solar months and 62 lunar months in 5 years. So, 2 additional lunar months. So, it is called intercalary months or Adhika Masa, okay. 2 Adhika Masas in 5 years. And concept of a Tithi, 1/30th of a lunar month is introduced, okay. So, these are the concepts which you are following even now in India. Tithi was perhaps introduced first year, you see. In fact, in the poster of the brochure of the conference, we said Ekadashi, Dwadashi and Trayodashi, okay, of Ashvina, Shukla Paksha, it is written, okay. So, that's got a definite meaning. So, Tithi. So, Tithi concept was, that tells you about what is the angular separation between sun and moon as observed from the earth, okay. So, the Tithi concept was there. So, that is, and Adhika Masa, you see, sometimes you have 13 lunar months instead of 12 lunar months in a year, you see, that is because if 12 lunar month is equal to 354 days and 1 year is, that 365.25 roughly, okay. So to bridge the gap, so 11 days gap is there. So you have to introduce an additional lunar month. Okay, so that is the concept of Adhikana, which is still followed in India. You see, from the time, in fact, it dates back even before Vedanga Jyotisha. So this Adhika Masa is there. So those concepts are used. Okay. So now the short algorithms are there for finding positions of sun, moon, tithi, nakshatra. Importantly, for finding the duration of daytime over the course of the year. What is the duration of daytime? That is sunrise to sunset. That is the daytime. Okay. What is it? That varies. You see. See, in Chennai, it doesn't vary too much. It is near equator. For in Delhi, it will be quite a bit. You see, the first time I came to, Kanpur in north, you see, from Bangalore, I was somewhat shocked that, in the winter, the sun is setting at 5 o'clock. You see, so early in the winter. So that is because it varies over the year. That depends upon the sun thing and all that. And I'll come to that. In the Indians, for the first to give a precise formula for that, how the variation happens. Okay. So they are assumed to be uniform. Okay. Here, the sun and moon are all moving uniformly in the stellar background. Okay. But are actually non-uniform in reality. So the computed values would be approximate to that extent. But after each yuga, the sun and moon come back together at the same position in the stellar background. That is the assumption. Okay. So like the cycle of seasons, but longer. So again, this is approximate, but the important thing is the concept of some kind of a cyclic time, which is still followed in India, right? I mean, this kind of a thing, that whole concept of time is cyclic. Earlier it was a short yuga of 5 years, then it is a Mahayuga of 43,20,000 years, and so on. Okay. So these central concepts are not changing. So because it is approximate, probably corrections were made. This is a simple scheme and simple mathematically to compute. So some scholars feel that, they made it simple, though they may have known that it is somewhat approximate, so that some corrections were made, in these things. The important thing is the sutra format. You see, that is the Indian way of doing things. So people had mentioned it. You see, you give the rules, you see, and then you explain the rules. So like in grammar, you have the Panini's Ashtadhyayi. There is a set of rules for generating the proper sentences in Sanskrit. Or you have the Chandas Sutra, the rules for, this prosody kind of a thing. Okay? So this kind of rules is there across the disciplines. And that is the sutra format. And in Vedanga, which is the first text in astronomy, mathematical astronomy text, which was followed later by other texts. Okay. So, and it is in verses. The Vedanga Jyotisha is only about 40 verses, so there are two versions, but 40 verses, so it is easy for persons to remember. Okay, that is the thing. So the algorithmic nature continues in the later Siddhantic texts, like Bharatiya, which was in 499 CE, it is composed in that. Brahmasputa Siddhanta, Siddhanta Shiromani, Tantra Sangraha, to name only a few. You see, there are many more Siddhanta texts, in which we now have a Mahayuga 43,20,000 years. After which, sun, moon and all planets return to the same position in the stellar background. Or after a kalpa of 1,000 Mahayugas, the other variables associated with planets like nodes and apogees also return to the same position. So we have the concept of cyclic time linked with Indian cosmological concepts. And in this Mahayugas, number of revolution of sun is 43,20,000. That is the definition of year itself is that, that 43 lakh, this number of years means number of revolutions of the sun in the stellar background. Moon is that number, Mars, Jupiter and other. So one can find average positions of the stars from these planets. From the sun and moon also were considered as planets. So it is basically a geocentric kind of a framework. So planets, sun, moon and planets are all moving, stars are all moving around the earth kind of a thing. So that is the conception. So one can find the average positions of the planets from these numbers. Okay. Now schemes should be devised to get non-uniform motions of planets. So that is why there the trigonometry is needed. So that is the thing. Now the Indian jya is so this is the thing. Suppose the circle is there, okay. So then this OBD, that is the straight line, and then OA is the straight line. The angle between them, what we call angle is this theta now, you see. And suppose the arc is AD, okay. So that is arc theta. Then drop a perpendicular from A to B. So that is the jya, Indian jya, okay. Jya is AB, is r sin theta. So in Indian trigonometry, this jya is a length, whereas normally, in modern trigonometry, jya is the ratio, is right, opposite side by hypotenuse. But it is same as modern sine and cosine except for r, you see, except for r, because of this length, this thing. So normally it was circumference of a circle is taken to be 21,600 units. So angle of 1 minute or 1/60th of a degree corresponds to arc of 1 unit. So r comes out to be around 3438. It's called trijya. Whereas the Greeks did with what is known as chords, okay. So here, you see, there is a arc AC, okay, connecting it to the straight line, that's called chord AC, okay. So that AC is the chord corresponding to the arc AC, and that is chord of 2 theta here essentially. So they are related, but there is no right triangle in the definition of the chord, no right angle triangle. So there is no cosine and all that. And soon it will be realized that Indian sine is far more convenient for writing formulae and computations, as we see, you see. So though they are, it means might have been inspired by the chord, concept of chord, but it is an entirely different distinct trigonometry. So that modern trigonometry is basically Indian invention, we can say that. Yeah. 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 So just to give you an example how the sine function comes, I don't want to be technical, but I will say that non-uniform motion, you see. See, if everything was uniform, then there wouldn't have been any, physics. No, because non-uniform motion is the beginning of this classical mechanics and all that, because only then the concept of acceleration, force, etc. comes, okay. So now understand non-uniform motion is a very important thing. So what they did was, that they had a concept of what is known as the epicycle, which is an artifact to explain non-uniform motion, okay. So suppose there is an object, a celestial object. So it is moving, to begin with you say that it is moving uniformly, okay. So that is P0. That's called a Madhyama Graha or mean planet, moving on a big circle of radius r, okay. There is a Mandocha whose direction is specified, okay. And the actual planet is in a small circle called epicycle of radius r, such that this is P0 P is parallel to some direction, okay. Basically some big axis of the ellipse. We know that the planets move around ellipses nowadays, okay. So it is something like that, okay. It eventually turn out to be that. So I don't want to go into too much of these details. So the mean longitude is this, gamma OP0, and longitude of Mandocha is theta m, okay. And minus delta theta, there is the correction, this is the correction, the true planet is this gamma OP, and this is called Mandasphuta. It is theta 0 minus delta theta, where delta theta is this, okay. So what you don't bother about epicycle model too much. So what I wanted to say is how the signs come. It is inevitable. To explain the non-uniform motion, you should have the sine inverse and all that. That's how it will come, okay. So this is the kind of formula. So epicycle model probably originated in Greek astronomy, but no such formula is there. There is no formula. I will come to that. Indians only had formulae. In Europe and all that, it came much later. And they had to use tedious use of tables to find delta theta, okay. So it is epicycle model, etc. is there in Ptolemy's Almagest and all that. So for that, to find out the non-uniform correction, to get the correct position, you have to, go from arc to chord and then back to chord to some other chord related to that to arc and so on. See, it's very tedious procedure. Whereas in India, straight away you have got this. This is a formula, you see. Inverse. So this is the formula. That is the important distinction. Okay. Yeah. See, for instance, as I told you, duration of daytime. When you want to find out the duration of daytime, okay, so then, sorry. Yeah. So the sun's diurnal path is there. At any given day when its declination is delta, that is when it is, removed from the equator. So then, one can show that its latitude to the place is phi, the declination is delta. You see the sun from the meridian to this, it is coming 6 o'clock circle, that is 90 degrees or 6 hours, but it has to travel some more to set. Okay, 6 hours plus something. And then the same 6 hours plus something the other side, you see. So the meridian transit 90 degrees plus delta alpha, and sunrise to sunset is twice of this, okay. And delta of alpha is this, sine inverse of this, you see. So this is given basically in Aryabhatiya, okay. Of course, he doesn't explain it fully. As mentioned, it is very cryptic, okay. It's very, very concise book, and Bhaskara one only had to explain it and all that for it to be intelligible to everybody. So this formula is there, but more detail you get Brahmasputa Siddhanta, Brahmagupta and all that, all these things are explained. So this is the duration of daytime, you see. And of course they didn't talk of degrees, they said Ghatikas. So finally, so the duration normally it is 30 Ghatikas when it is, on March 21st or September 23rd, that is when it is the equator, plus or minus this, you see, 1/6 delta. This is the formula. So the very formula is there, you see. Of course, it is written in terms of verses, you see, and they will express it differently. So what they will say is, sin phi. So they will not say sin phi. They will say that, akshajya. Akshajya is multiplied by krantijya. Krantijya is divided by lambajya, and that was further divided by jujya. You are laughing. And then you take the chapa of that. But it is essentially equivalent to a formula. Okay. Yeah. So importance of Indian Jya was recognized, you see, by at least the historians of mathematics of yesteryears. So one Sarton, he says, handling of science is much simpler than that of chords. Our trigonometric formulae, both plane and spherical, are relatively simple and elegant because of their symmetry. Similar formulas based on chords would be more complicated and less elegant. Nobody had the courage, however, to deduce them formulas based on chords, because the Indian science drove the Greek chords, drove them away forever. You see, this is, I got it from a thesis of one famous historian of mathematics called Sriram. And of course, Sriram adds, just as, the Indian number system drove away all the other systems, you see. So, this is the important. And one Boyer, he says, thus was born apparently in India the predecessor of the modern trigonometric function known as the sine of an angle, and the introduction of the sine function represents the chief contribution of Siddhantas to the history of mathematics. And again one Bond, he says it was by the use of Indian sine that the Arabs were enabled to build on the Greek formulation of auxiliary trigonometry of the chords, the complete and independent trigonometry of the sine. So the most important thing is sine is considered as a function, okay? So at any given time you find out the mean longitude, you get the correct true longitude using the sine function. So that is you are written as a formula, you see. So that is only possible because of, the Indian approach, yeah. Now, it was because the Indians expressed the true longitude of a planet in terms of sine function that they could think of finding an expression for the rate of motion of a planet also as a function, which is the derivative of the longitude, okay. So from the earlier expression for this, we had this, The Mandas Puta was this, and approximately theta 0 minus r 0 by r sin m. Okay. Using the concept of a derivative now, okay, we can immediately, what is the problem in deriving the derivative of sine? Sine is cosine, okay. So you get this. In Mahasiddhanta of Aryabhata 2, he is called Sputagati, the true rate of motion. Sputagati is equal to Madhyagati minus Kotiphala of Mandakendra into Mandakendra Gati by Trijya. So he gives the formula. And even before that, Manjulacharya had given that. Okay. So, because they could write it in terms of the sine function, they could find out the rate of motion. But if you just always, stick to geometry, okay, and write, geometrical model for these things, you will not even think of writing, an expression for the rate of motion. You will think that you have to do more and more complicated geometry and all that, you see. And that's what they did. And that is what even Newton Baba did. Newton, he is supposed to be the discoverer of calculus. I heard some European scholar talking about Newton. Okay, this is in 17th century. He said, I have not read Newton's Principia, not even translation. So he said that there is no formula in Newton's Principia, and all these things, all these treatments are completely geometrical. And one more thing, we think that Newton was a very great person. Of course, he was a great person, who changed the course of this thing. But he had a deep amount of admiration for the old Greek tradition. Okay, so the Greek, we should learn from them. He had deep admiration for and he has used all these old Greek methods of geometry to deriving various things, complicated things in mechanics. So that is the thing. But here we have a straight away this kind of a formula. Okay. Later, Bhaskaracharya, of course, he explains things more in detail. So he discusses the instantaneous rate of motion in Siddhanta Shiromani. He says, the true daily dinantara spashta khagantaram syad gati sputa tat samyantarale koti phalagni etc. Tijyoduta karki mrugandikendra taya yutona graha madhya bhuktis tatkaliki manda parisputa syat. Okay. So he said the true daily motion of a planet is the difference between the true planets and successive days. Okay. So how the position is changing. So you see it sunrise at one day and next day kind of a thing, So you will get a rate of motion, okay? And you take it as some kind of, as if it is uniform throughout. But he's not like that. He says that the Kotiphala is multiplied by the rate of motion of Manda and Amali and then added or subtracted. That is because they used to take only the magnitude of cos. So you know that the cos is, in the first quadrant and fourth quadrant it is positive and things like that. So that has to be taken into account, So that's why he said, yuta una, okay, you are added or subtracted. That is only a small technical matter. So he is saying precisely this, he is giving this in a shloka form. And there is detailed explanation of this in his commentary. And note the use of term instantaneous rate of motion, tatkaliki. Okay, so we credit instantaneous velocity to Newton, okay, and that is considered as one of the major advances. But instantaneous rate of motion is already there. Bhaskara discusses it. In fact, he discusses it more in his Siddhanta Shiromani, more than 5 centuries before Newton. Okay, so the above method for finding the instantaneous rate of motion is satisfactory for Sun and Moon. For planets, it is more difficult. Okay. So, we need not go into the technical details. He discusses the problem and there were some ways of doing it. People were doing it even before Bhaskara, but he says they were all, they were not getting correctly. So, Bhaskara notices the flaw. He says that a new approach is required. And with some ingenious geometrical reasoning combined with trigonometry and calculus ideas, he had the calculus ideas. He arrives at the true velocity of a planet. So this is exact in the Indian framework for planetary motions. Okay, so that is not a retrograde motion and all that. Sometimes that planets go forward or backward and all that. It's not an easy thing. Okay, So that he does by using a new approach. I can't do this thing, but he gets the calculus ideas are there and kind of a new approach is there. All these are not given due credit in the international history of science narratives of the correct times, of the current times, okay. So they are, earlier we thought that there was some admiration and all, but now somehow they are not, they don't even pay attention to what was there, you see, what many people have said, you see, in 1930s or 50s or 70s or what some of us are this thing, they don't pay attention, you see, that is all. Because they are obsessed, Greek ka ho gaya, then afterwards Arabs, okay. They are completely up, and before Greeks, Babylonians, you see. They are only interested in that, you see. So it is our duty to build a narrative, Indian narrative kind of a thing, I mean, it is like, if Indian music, you see, so it may not be appreciated by Westerners. So what? I mean, they don't care, whether you appreciate, the Western classical music, right? Do they care? I mean, of course, they may be nice and they appreciate you if you appreciate that. But you see, we don't have to bother, and you get greatly elated, if some, they say make some appreciative comments, and, become dejected if they make some negative comments. See, one has to build up one own narrative. I mean, in any Indian discipline. So that is I think that is, I am sure most of the scholars here will certainly agree. Okay. Now, this is only the algorithm. Was it just algorithm, rule and all that, or more? Okay. So, the practitioners of astronomy were supposed to have the algorithms at their fingertips. Okay. So, Aryabhatiya, it is, those days it would have been very easy to mug up. Only 129 one verses. And that is only about 240 and odd short lines. Right? That is all. You see. So, it would have been easy to memorize. And even Bhaskara's Siddhanta Shiromani, it is about 460 verses. So, it may not be very difficult. You see. A few months one can, memorize all the algorithms. But that is not the only this thing. One has to go beyond that. So they used to have they have to know the algorithms that they have the knowledge at their fingertips. And Karna texts actually focus completely on computations, simplified as much as possible, suitable for day-to-day applications. But a great astronomer like Bhaskaracharya emphasizes the need for practitioners to understand the rationales of the procedures. He himself derives or gives upapattis for all the algorithms of his Siddhanta Shiromani in his auto commentary, Vasana Bhashya. Okay? So the explanation have to be understood, you see, not just mug up and cram. Okay? So one has to understand all the rationale and all the detailed reasoning. So that's what And he says in one of the places in Siddhanta Shiromani, says, Janan Jataka Samhitaha Saganita Skandeka Desha Api Jyotish Shastra Vichara Sara Chutra Prashneshva Kinchit Karaha. Of course, it's beautiful poetry. I may not be saying it very well. Yah Siddhantam Ananta Yukta Vitanam No Veti Mitto Yatha Raja Chitramayo Thava Sugatitaha Kashtasya Kantiravaha Garjat Kunjara Vardita Drupachamura Api Urditashvadikaihi Udyanam Chuta Chita Vukshamatava Pato Vihinam Saraha Yoshit Proshita Nutana Priyatama Yadvanna Bhatya Chakaihi Jyotish Shastramidam Tataiva Vibudaha Siddhantahinam Jaguhu. So what he is saying is, by mastering only one branch of astral sciences, namely Jataka is mainly Phalita Jyotisha, astrology, Samhita or omens, you see, the Bruhat Samhita is full of omens, this thing, or Ganita, that is the mathematical astronomy. One cannot answer so many intricate problems pertaining to it. Such a person who does not know the theoretical part of the astral science, which abounds in innumerable reasonings, is one like a king depicted in a drawing. You see, a king in a drawing is just that, it is drawing, okay? Or a lion which is made out of wood. Intelligent people say that the science of Jyotisha without the Siddhanta is like a king's army without roaring elephants, though excelling in horses, etc. You see, you may move fast with horses. You see. It is like a garden without mango trees, or like a lake without water. And again, like a lady parted with her newly married lover, you see. So that they always make these things quite interesting. The sutra format, or coming to the end of my talk, the sutra format or algorithmic nature of Indian astronomy is well known. Okay. Okay. In fact, a very word algorithm is, it derived from Al-Khwarizmi, the Central Asian astronomer, right? Islamic astronomer. But actually, Al-Khwarizmi studied many Indian texts. You see, it had been introduced even earlier. He must have been in, I think, the 9th, 10th century. Before that itself, Indian mathematics and astronomy had reached the Islamic Arab areas. And he wrote a book on the Hindu method of reckoning. Okay, Hindu method of calculations and all that, you see. So he was inspired by that. And so, though algorithm is, derived from Al-Khwarizmi, it has deep-rooted Indian connection, because Al-Khwarizmi himself was deeply influenced by the Indian methods. Like most Islamic Arab mathematician astronomers before 8th, 9th century. So, commentaries are very important, and they describe the algorithms in detail, and more importantly give the upapattis or rationales or derivations. They may not be exactly like, the Euclidean method of, have a set of assumptions, axioms, and then derive all the rules. It is not like that. Any reasonable kind of explanation, you see, which is completely logical, and with demonstration and suitable diagrams and all that, which will convince a person, that is called an upapatti. So, a later work, Ganita Yukti Bhasha of Jeshtadeva is entirely devoted to rationals. You see, it is a book which is related to rationals, and that is where, we learn, how exactly the Kerala astronomers, mathematicians, you see, they understood the sine series, cosine series, infinite series for pi and all that, you see. So that how exactly they understood it, how they derived it, they are all in this. And it also talks about planetary models and all that in detail. All rationales only, you see, proofs. And we have sine as a function. So you have formulae for various variables, and they are far ahead of times. See, as I told, there are no formulae in Indian, other civilizations. You see, here you got a ready-made formulae kind of a thing, because sine is a function, and from that, you write the positions of planets in terms of the sine function and other variables. You write the various how to find out the shadow corresponding to a given time. You write a formula for that. For eclipse, you see, when does the eclipse actually occur? You see, you give a procedure. And the middle of the eclipse, and when does it start, when does it end? All these are given in terms of formula. Okay. So they are far ahead of times, and they could think of calculus ideas in finding rates of motion and all that, because of this, writing in terms of sine as a function and other things as a function, and they could think of instantaneous velocity. There is continuity as well as evolution. Bhaskaracharya consolidates the work till 12th century and takes it forward. So Bhaskara's Siddhanta Shiromani was in 1150, 1150 CE. And Kerala school of astronomers, Nilakanta Somayaji, etc., they 14th to 17th century, and even elsewhere, take the tradition even further. In fact, it is quite a living tradition, even, let us say, till 19th century. There is one famous Chandrasekhara Samanta, Oriya astronomer, or Patani Samanta. There is a Patani Samanta planetarium in Bhubaneswar. Okay, so he might be, in one way, he can be considered the last great Indian astronomer in the Siddhantic traditions. He devised some experiments, he devised some instruments to do various kinds of, measurements on planets and moon and sun and all that, you see. So, he worked in the Siddhantic tradition, though probably he knew about the modern European invasions. It's already, see, he wrote his Siddhanta Darpana around 1860 or so. But he wrote it completely within the Indian framework. And so, and some other places also, that they take the tradition even further. One more important aspect is that there are, works in regional languages. For instance, many of the Kerala works are in Malayalam. Apart from that, there are many other, there are many commentaries and, texts, mainly calculation manuals in later in Hindi, then Kannada, then Telugu and all that, which are, come even from 16th century or so, you see. So this is, that is the kind of propaganda we have, that they are all confined to a few people, okay? In India, they are all confined to this, they wouldn't let us these things, It was completely far removed from ordinary people. That is not complete, it is completely wrong. Because there are serious gradations of text. There's, Tarana text and all that, which used to be, practiced by a large number of people. And when is the main, text in a modern European language? There's only in 17th century beginning. Galileo was one of the first. Even Newton wrote only in Latin, right? I mean, even after Galileo, Newton wrote in Latin, not in English. And Galileo, around 1600 and all that, you see, he wrote he was the first to write in these things, in Italian. And around the same time in India we have, in Malayalam there are several texts on mathematics and astronomy in the Malayalam language. And many other places also, there are texts, on not very maybe great works, but certainly explanatory kind of works and calculation manuals in the regional languages. So that is also an important feature. I think I will stop here. Thanks a lot for the very patient audience.